Okay. Let's talk about what a table of reduction potentials can give you. I took 3 samples off the table of reduction potentials. So these are the only ones we're going to include for the purpose of the questions I'm about to ask you. But if you're given a complete table of reduction potentials, there's a whole flurry of questions I can throw at you just because you have all those numbers. I can ask you to calculate standard potentials. You might also use it to calculate non-standard potentials. But now we've got a few other questions I can ask you as well. All right. So first off, I might ask you, which of these species is the strongest oxidizing agent? Which of these species is the strongest oxidizing agent? How many chemical species are on the board right now in this mini table right here? There's 6. 1, 2, 3, 4, 5, 6. And so if I'm looking for the strongest oxidizing agent here, in fact, we'll just do it right below. Well, what happens to the strongest oxidizing agent? It gets reduced. It gets reduced. So let me ask you a question. Who's getting reduced here, Al3 plus or Al? Al3 pluses. These are written as reductions. Notice electrons are on the reactant side, so these are reductions, and it's the reactant that's getting reduced. So Al is not even a possible answer to this question. In fact, none of these 3 is a possible answer to this question. Now, if we look at these reactions going backwards, what could happen to Al going backwards? He'd be the reactant going backwards in what kind of reaction? That'd be an oxidation, and so he could potentially act as a reducing agent. And so here, we're looking for an oxidizing agent. It's got to be one of these 3. If I'm looking for a reducing agent, which gets oxidized, it's got to be one of these 3.
So is that just like a rule of thumb?
Totally rule of thumb. So, because again, the key is, oxidizing agents are the species, only can be a species that gets reduced. And so the strongest oxidizing agent is whichever one gets reduced most spontaneously. Which of these 3 gets reduced most spontaneously? Ag+. And Ag+, out of these choices, is definitely our strongest oxidizing agent. Okay, and I can't spell strongest apparently. Let's go the converse as well. Strongest reducing agent or strongest reductant. Now that I'm talking about the reducing agent, I got to talk about things that get oxidized. But these are all reductions. So I'm not looking at these 3 reactions. I have to look at them all backwards, running in reverse. And if I'm looking at them all running in reverse, what does that do to all the signs? Flips them all. And so in this case, my only possible answers for strongest reducing agent are Al, not Al3+, Ni, and Ag. These guys are the reactants in the oxidations that run backwards. Which one is the most spontaneous? Al. Because running backwards, that would be a voltage of positive 1.66. And so Al metal, again, not Al3+, would be the strongest reducing agent. The last kind of question you get is I might say, which of the following would react spontaneously together? Which of the following would react spontaneously together? Guess what kind of reaction I'm talking about in this chapter? Redox. Good. Not oxidation, not reduction. It's oxidation reduction, which means I have to mix one of these, because they can get reduced, with one of these, because they can get oxidized, for this to even be possible. Notice, if I just said, can Al3+ react with Ni2+ based on this info? Well, what can happen to Al3+? He can get reduced. What can happen to Ni2+? He can get reduced. You ever heard of a reduction reaction? Nope, sweet. That's just right off the bat wrong. And we just say a big fat, no, these will not react spontaneously. I don't have to do any number crunching or anything. Yeah, I need one from this side and one from this side, because these guys can gain electrons, these guys can lose electrons. Well, it's going to matter. So let's say now, I say I mix Al3+ and Ni. Al3+ and Ni. What can happen to Al3+? He can get reduced. What can happen to Ni? He can get oxidized. Ooh, so redox is possible. But now I have to say, is it spontaneous? Now that I at least have a chance, now I got to do some number crunching. When Al3 plus gets reduced, what's the voltage? Negative 1.66 volts. When Ni gets oxidized, what's the voltage? Positive 0.25. Awesome. Would they react spontaneously then? No. So it's still a no, but I had to do a calculation to figure it out now. And so finally, if I mix Al and Ag plus, so Al can get what? Oxidized, backwards, and Ag plus can get reduced. So this is a possibility. And now let's do some number crunching. When Al gets oxidized, what's the voltage? Positive 1.66. And when Ag plus gets reduced, what's the voltage? Positive 0.80 volts. And when you add those together, will this get spontaneously oxidized? I'm sorry, will this be a spontaneous redox reaction? You bet. Question? Yep. When the total is positive voltage, that's when you know something's spontaneous. And so the question again was, which of these pairs will react spontaneously together? And so first I just had to make sure redox was even a possibility. And if it was, then I had to do some number crunching to make sure the voltage came out positive.
So then would Al and Ni2 plus also?
So Al with Ni2 plus would also react spontaneously. So there's multiple possible correct answers. Hopefully only one of them or two of the above, or on a multiple choice test, it could show up in a number of different forms, but one right answer typically, right? Exactly. So let's put this all together real quick. If a reaction's spontaneous, what from the thermodynamics chapter do we usually use to figure that out? Delta G, and what do I want delta G to be for a spontaneous reaction? Awesome. Big fat negative number. From this chapter, we also learned that we can now look at the cell potential, and we want that to come out positive. Okay. But it turns out there was another way to know. And you guys learned this a while back. When Q is less than K, that means that the reaction needs to shift to the right. And shifting to the right means it's spontaneously going to the right. If you recall, I wrote it as Q less than K because this is how we'll often look at it. But how did I tell you to write it to figure it out? Alphabetical order, which K is greater than Q, and which way that mean it shifts? To the right. And again, shifting to the right means it's spontaneous left to right, as it's written. So any one of these three being true would mean it's spontaneous. Now here's the deal. A lot of students are like, well, what if delta G is negative but E is negative too? That's not possible. If delta G is negative, then E will be positive. They're mathematically related. They're interdependent upon each other. So if you look at the way this works, delta G equals negative NFE. So F is just Faraday's constant. We'll see him show up quite a few times. It's 96,500 coulombs of charge on a mole of electrons. So it is the total charge in coulombs on 1 mole of electrons. That's his constant. You don't have to memorize it. It'll be given to you. But you should know what it is. It's the charge on a mole of electrons. So that gets plugged into here. N is the moles of electrons in the balanced reaction or in the balanced half reaction. Great. And this is the relationship between delta G and E cell. If you notice, F is a positive constant. Moles of electrons are always positive. And you got that negative sign. If E is positive, then when you calculate delta G, it would come out negative. If one of these is true, so is the other one. Cool. So it's not like all three of these have to be true. If you knew that any one of these situations was true, you'd know the reaction is spontaneous. Cool. If you guys recall this equation as well, delta G equals negative RT ln K from last chapter in thermodynamics as well. So, and if you take the Nernst equation for the condition of equilibrium, you can get a similar expression here where E equals 0.05916 over N log of K. for the condition of equilibrium. So similar to what we did with the non-standard delta G, I did it for the Nernst equation reaching equilibrium as well. So here's the deal. There's 3 equations here, and there's 3 questions that I could ask you. I can give you any one of these 3 and expect you to be able to calculate any of the other 2. If I give you K, then I can say what's E. And technically, that's my bad. This is E standard and delta G standard. The top one could be standard or non-standard, either way. I'm just going to put them standard for the fun of it. And let's get that correct here as well. But here's the deal. I give you one of these 3, I can expect you to solve the other 2. I give you KEQ, I can expect you to get E standard. If I give you KEQ, I can expect you to get delta G standard. So if I give you delta G standard, I can expect you to get E standard. If I give you E standard, I can expect you to get delta G standard. So any one of these 3 is given. From these 3 equations, you should be able to calculate either of the other 2 that I ask you. Question. Moles of electrons, they're either going to give you a balanced reaction or a half reaction. So notice, what if I said, what is the delta G standard for this half reaction? Well, if it's a half, life is good. N is 3. So, and you'll plug in negative 1.66 volts right there. N is 3, F is 96,500. Factor in the negative, and you get delta G standard. Comes out nice. Now, one more thing. A volt, if you guys recall, a volt is a joule per coulomb. And so when you plug in delta G, you better make sure delta G is in what units? Joules. Because what do we usually give it to you out of a book from? Kilojoules. So make sure he's in joules before you use these equations. Be careful.